we would like to get extrema of this function. So what we do first is we will calculate the partial derivatives, and they come out to be complicated. So we are going to do what? Use MATLAB for this, because as you can see, uh, if we set these two equations to 0, at the moment they look pretty humongous. And even if we cancel this non-zero factor out, okay, still they look quite complicated. Or let's just see if we can simplify them further. Or you can see that I'm not doing any of them by hand. So one of the equations is this, right? Okay, and the other one, let me simplify that for us rather. Okay, so I'll say expand. So what we get is the other equation is this equation, and well, we have one solution. That's where all our work paid. Oh, sorry about that. Okay, we have at least one solution to these two equations, and that is which one? 0, 0. The other one, yeah, why don't we go to MATLAB when we have that available? All right, so let's go there. So now remember, we are using Livescript instead of just typing in the command window. So let's ask for new Livescript. So here is our new Livescript. So first, let's just give it the symbolic variables x and y, and then we are going to define our xy to be x to the power 4 plus x times y minus y to the third power plus 1, and that times the exponential of negative x square minus y square. Okay, so we have defined the function. All right, and then what we will do is let's just go ahead and look at a graph of this function. Or let's just do this. Let's define fx to be the derivative of f with respect to x, then define fy to be the derivative of f with respect to y. All right, and then we will go for fxy, right? So we go for fxy, that's going to be what? The derivative of fx with respect to y, then fx, then this is the derivative of fx with respect to x. Okay, and now we are almost there. I could have typed all these up, but we never did a question like this, so I thought that we would go ahead and I would go ahead and type that, and or you could have fast forwarded it. Okay, so here, so we have all the key things defined here, right? And then let's see what they tell us here. Okay, so here we go. All right, we have all the outputs. So now what we can do is that we can ask it to evaluate all these second derivatives at 0, 0, so that we can decide whether we have a, whether we have a max or min or saddle point there. And I don't know why I'm panicking like this, because I have a meeting coming up. All right, so let's see what we got here. Let me pull this to the left for you. So So if we go ahead and take these values into our discriminant, that is into this quantity at 0, 0, we get 4 minus 1, that is 3, which is greater than 0. So we fulfill one of the important requirements, okay, for max min of two variables. And then what we have is, we just saw, I'm just writing it again, that this value is negative 2. So what we shall have is, we shall have a local, excuse me, local max at 0, 0, right? And then for the other one, what we will do now is that we will go back to MATLAB, okay? So first, let's just go ahead and make a graph, and I'm just going the easy route first. So I said fsurf, so graph should be coming up. Please come up, graph, okay? Okay. And remember this, whenever I do this, that is whenever I am entering a command, I press Control Enter, okay? I mean, we went over those in our earlier, videos, and we can do this also. You can see that is at 0, 0 looks like, this is our max, and this appears to be going to become a global max. Why? Because this factor is the dominant factor, and as x, y go to infinity, like as we go to, towards infinity from all over, I hope I'm speaking correct English, all right, that will pull it to 0. So here we have a max at 0, 0, and here we have a min, all right, which is about negative 0.27. All right. So, but we want to calculate it. Now, in case you want a better looking graph, let me just tell you what to do. So first notice that like we are too far out. So what we would do is that we shall, let's just restrict it to negative 4, 4, negative 4, 4. And then now they have changed the name, you know, to mesh density. Okay, it did say density when I wanted mesh, yeah, here, mesh density, which by default, I think they keep it at like 35 or so. So let's make it like 60, okay? And again, I'm doing Control Enter. Let's see how does the new graph look like, okay? All right, so new lab graph looks much smoother now. This is your max here, and here is your min. And now let's also look at a contour plot. I mean, we know from here we can read the min approximately, right? Okay, so anyways, and another way to do this is that just take it to the figure window. So if you go to the upper right here and click on this, then the graph will open up in the figure window. And now you can see a much better copy of the graph, right? Okay. And so here is your max and the min is here. Let's go ahead and look at a contour plot also, because in this one things are very clear, but sometimes you may need more information. So I'll make a contour plot for you. So for the contour plot, let's go back to our command window. Okay. And the way to get contour is this, that f contour is, I used to do it in a different way before, but now what you will do is you want the contour plots of what? The contour plots of f, and we will keep it in the same range. Okay. And then we are just going to give it a little wide line width. Okay, so let's for line width. And for this purpose, 1 should be all right. Okay, and then let's also give the line a color because I like doing, just a second, line color, because I want the line color to be black, and the only way I know how to do that here is in hexadecimal. And now this part is very important because we are, making a contour plot or different levels. So it's important to give different set of values for this function for which it will plot the graph. So remember this, we saw that the minimum value was about negative 0.27 if I remember it right, and maximum is near 1. So I'm starting at negative zero point 0.5 and going in the steps of 0.05 and then up to 1 just to just to obtain the various curves. All right, so now I will do Control Enter, and so we have our graph. If we want, we can also do this, that we can give it like more levels near this, because now we already know at 0, 0 we have a max. So I'll just go back as I did before to the figure window. Okay, so let me just bring it from the figure window right here. Okay, so and what we would do is that we will go ahead and estimate a point near here. Now, to get a denser contour plot, what we can do is this if we want. So we can see our other point of extrema is here, that is between the x values of -1 to 1 and the y values, say 0.5 to say 2. So we can go back to our script. Let me bring the script back to you. What I will do is that I shall repeat the same line here, okay? And so in here, we are going to go from negative zero point 0.5, then 0.01 to 1, change this from negative 1 to 1, this from 0.5 to 2, right? And now let's press Control Enter and see what we get. Okay, so we get a, yeah, we get a graph here for the other one in which we can go closer to it. Okay, so let's bring it from the figure window. Now we could have made these denser and these like sparse, but that's okay. I think we have enough to go with. So here, if we see the points are like close to, say it's negative 0.3 and 1.32 to start with. If we want to get the solution, the other solution, one solution was 0, 0. Okay. So our objective is to solve these two equations, which were a consequence of setting the partials with respect to x and y equal to 0. So we shall use a numerical method, okay, and we will give the numerical solver starting point of x equals negative 0.31 and 1.32. So let's just go back to our live script. So what we are going to do here is that we are going to use a feature that is called fsolve, all right, and that is available if you activate the optimization toolbox in your MATLAB. Okay, so to use fsolve, which by default uses trust region dogleg algorithm, which will work in our case. All right, so in this case, what we first do is that we take these two expressions as an anonymous function. So the way we will do is this, that we'll say, okay, z at xy is same function that we had in the same style as we had f at xy, right? And now what I will do is that I shall type these two functions. So let me type these and bring it back to you. So here I typed this and this, these two expressions, okay, into this bracket for this anonymous function. So here is the first function, then I separate by comma, and then I go to the second one. And now I'm going to use fsolve. What I would do for fsolve is that define a second anonymous function to combine x and y into a single two-dimensional function argument. So what we would do is, yeah, let's define another argument u, okay, and then we will go z, and then the two components, right? So we got u2, okay, and then we are going to write our initial guess, and that we write in closed brackets. Okay, so that's negative 0.31, then 1.32, and then control enter. All right, so hopefully we should have, sorry about that, hopefully we should have an answer for our question. So the approximate solutions are x equals negative 2.2947, y equals 1.4117. Now we shall just substitute these into the function and get the minimum. So let's go to our function and then give it the x value negative 0.2947, y value as 1.4117, control enter, okay, and then it should have a value, okay, well, it's in the exact mode. We can do this for decimal approximation. We can just say double and then give it this link right here. So we got this, and so the z value is, how much is the z value? It's negative 0.2776, okay? And we found that the max is 0, is that x equals 0, y equals 0, and z equals, all these are 0, this is a 1, this is a 1, so the max value is 1, and we used the fsolve feature of MATLAB to get for the minimum the x coordinate of negative 0.2947. Here you can see that that's how we are aligned the x coordinate as, pardon my handwriting, okay. Then the y coordinate is 1.4117, and for the z coordinate, let's erase this here, okay, we got negative 0.2776. So that's approximate minimum, 4 digits after the decimal sign. Let me create something similar in a shorter video for you.